Welcome to this video. This is the first video in a series of videos which I hope to make covering some of the details of Leonhard Euler's Introductio in Analysi Infinitorum, an introduction to the analysis of infinities. I don't know how many videos the series will consist of, nor do I know yet how much of the work I'm going to be covering, but I currently have plans for at least 2 videos. The first video, this one, will be covering chapters 1 and 2 of the first volume, and the second video will cover chapters 3, 4 and 5. I'll see how I feel after the second video, whether I go ahead and make any more. I want to present Euler's work as much as possible in the way that Euler presented it, and the point of this video is to try to understand the contents of this book from Euler's perspective, not from a modern day perspective. That means, of course, that some words that Euler uses, such as function, may not have the same meaning as they have in modern or contemporary mathematics. Euler often uses techniques that are not typical of modern mathematics and so on. Wherever possible, I want to draw attention to these differences and in doing so hopefully arrive at a better understanding of Euler's work. Just to be clear, I've made these videos in the first instance for my own benefit. That is, for me to better understand Euler. These videos are not intended to be self-contained or comprehensive in any way. The contents of the videos may seem to be in need of some tidying up. However, I wanted to make these videos in order to make available to others the notes that I've made for myself on this particular work, and if these videos help a handful of other people to better understand Euler, then I'm happy. I'll be working from the original Latin version of this work and providing translations into English of certain parts where relevant. In my opinion, the ideal is to always read a work in the original language in which it was written, wherever possible, because these words are the words that the author chose to write, whether consciously or not, and therefore to me most accurately represent the author's original intentions. Of course, this is just an ideal. Learning languages is a very time-consuming process, and even someone who dedicates their entire life to doing nothing but learning languages will only ever manage to learn a fraction of the total number. So I've reached a compromise. I've translated the words from Latin into English as best I can, but I've decided to leave the mathematical symbols unchanged wherever possible, in order to preserve as much as possible of Euler's original work. I won't be giving a full comprehensive translation of the work though. The translations provided in this video from Latin into English are my own translations. I'm not a professional translator, and nor do I have a formal education in ancient languages. What I do know of Latin is what I've picked up from books and YouTube videos, therefore I can't guarantee that the translations are correct or even good. They'll simply be the best that I've been able to produce at this moment in time, and unsurprisingly may sometimes be quite amateurish. Indeed, I found some parts difficult to translate. Of course, I'm open to constructive criticism regarding my translations. If at any point I need to say anything in Latin in this video, I'll use the ecclesiastical pronunciation rather than the restored classical pronunciation, or at least as close as I'm able to get to it. This is simply personal preference. Most of what I listen to in Latin is in the ecclesiastical pronunciation, and so it's the one that I've naturally acquired. Again, I can't guarantee correctness of pronunciation. I tend to be very sloppy with vowel lengths and so on, so if my pronunciation offends your ears, then please either give me some constructive feedback or watch one of my other videos on my channel where I don't try to speak any Latin. I won't be systematically going through the book line by line, rather I'll be covering some of the more noteworthy points. Some chapters I'll go through in some detail, and other chapters I'll only briefly cover, and what counts as noteworthy will be according to my own judgment. Sometimes I may skip some chapters entirely, and I may have to skip backwards and forwards from time to time. I'll comment on some of the more interesting sections, definitions and theorems, and omit some of the less interesting. I'll also draw attention to some of the uses of notation and language wherever I feel that there's something worth saying that might facilitate understanding. What we will see is that Euler relies heavily on intuition to prove or justify some of his results, and his proofs certainly do not have the same level of rigour that we'd expect from contemporary mathematics. That's simply the way that things are though. For some parts that Euler doesn't provide a proof for, I'll sometimes provide a proof, but in these proofs I'll try to retain some of the style of Euler, and so to do this I may have to use techniques which might seem a bit suspect to modern sensibilities. Euler, of course, does assume that some things are already known from the outset, and therefore there are some things that he doesn't prove. The algebraic techniques that Euler uses often seem fairly elementary from a modern perspective, but nevertheless Euler uses these techniques very creatively and with great effect. So enough with the introduction, let's get started on Chapter 1. Chapter 1, on functions in general. In this chapter we find some important definitions, starting with some definitions of different types of quantity. As will become clear, the definitions that Euler gives are not always precisely formulated. I'll simply be presenting the definitions as they're given and will not necessarily be critiquing them, but I may make some miscellaneous comments about them from time to time. This chapter also discusses functions and different types of functions: analytic, transcendental, rational, irrational, integral and fractional, as well as single and many-valued functions, and odd and even functions. Some of the basic properties of these functions are also explored. Section 1. A constant quantity is a determinate quantity which continually maintains the same value. Section 2. A variable quantity is an indeterminate or general quantity which encompasses all determinate values. Section 3. A variable quantity is determinate whenever some determinate value is assigned to it. Therefore, a variable quantity includes absolutely all numbers: positive and negative, integral and fractional, rational and irrational, and transcendental. Imaginary numbers are not excluded from the range of significance. Now we move on to some definitions of functions. Note that Euler has a much more restricted conception of function than modern mathematics uses. Modern mathematics tends to think of a function as a certain kind of relation between the elements of two sets, which may have, but doesn't necessarily assume or require, properties such as continuity or analyticity. The notion of a set, certainly in the modern sense, didn't exist in Euler's time. Euler's notion of a function is not necessarily very sharply delineated, and so what is and what is not considered as a function could end up being quite subjective and varying from one author to another. Section 4. A function of a variable quantity is any analytic expression composed of the variable quantity and numbers or constant quantities. Euler often gives some concrete examples to illustrate the definitions, which goes some way to clarifying what he intends by his definitions, but often total clarity is not forthcoming. In this section, Section 4, we see a few examples of what Euler means by a function. What's meant by analytic expression is not anywhere, at least in this work, explicitly defined by Euler. The text of Section 4 continues: therefore, all analytic expressions will be a function of z, in which, except for the variable quantity z, all constituent quantities are constants. And a short digression at this point. In this section, in the Latin text, we see that Euler uses the phrase ipsius zeta, where in English we would write of z. And thus we have functio ipsius zeta, meaning a function of z. The word ipsius here is the feminine genitive singular of ipse, which normally translates as something like self. But here it's more natural to translate it as of. The word ipsius is simply being used to indicate the genitive case. To just write functio zeta could be taken as meaning that the function in question is z, rather than is a function of z. This is of course because Latin uses cases to indicate the grammatical function of a noun, and here in particular the genitive case, to roughly express the word of in English. The noun zeta is not declinable in Latin, and so some way is needed to identify the case where it's not clear or obvious. A similar technique for identifying the case of a non-declinable noun, a single letter symbol for example, is used by the Polish logician Stanisław Leśniewski, and so this seems to be a common way of expressing the case of non-declinable nouns in languages which have a noun case system. Zeta is a quantity, quantitas. Quantitas is a feminine noun in Latin, and hence the feminine forms of ipse are required for agreement with zeta. We also see on page 72, quicunque valor ipsi z tribuatur, whichever value is assigned to z, where ipsi indicates the dative of zeta. Note that when zeta is intended to be in the nominative, ipsa is not used, nor is ipsam used in the accusative, especially when the case is indicated by a preposition from which the case can be clearly discerned. For example, on page 10 we see in Theorem 16 per zeta, where per indicates that zeta, is necessarily in the accusative. Moreover, we also see on page 61, Functio ipsarum x et y. Ipsarum, the feminine plural genitive of ipse, agrees with the quantitates, quantities, x and y. We also see in section 4 Euler using the notation zz rather than z squared. Euler does use both notations throughout the work and similarly for other letter-like symbols, but I've not been able to determine the reason why one notation is sometimes used and other times the other notation. This notation is not extended to higher powers. So then Euler defines certain classes of functions, starting with algebraic and transcendental functions. Functions are divided into algebraic and transcendental. The former are those which are composed of algebraic operations only. The latter are those in which there are transcendental operations. Algebraic operations are, as stated in section 6, addition, subtraction, multiplication, division, raising to a power, and extraction of roots. Transcendental operations are exponentials, logarithms, and innumerably many others besides. Section 8. Algebraic functions are subdivided into rational and irrational. The former are those which do not involve irrational operations applied to the variable quantity. The latter are those in which radical symbols are applied to the variable quantity. Therefore, in rational functions, operations other than addition, subtraction, multiplication, division, and raising to powers where the exponent is integral do not appear. Section 9. Rational functions can be further subdivided into integral and fractional. In the former, there are no negative powers of z, nor expressions containing fractions in which the variable quantity z appears in the denominators, from which it is understood that fractional functions are those whose denominators either contain z or where negative powers of z occur. We're then given two general formulae for integral functions and fractional functions respectively. And I think by this general expression for integral functions, Euler intends a finite number of terms, since we see at the start of chapter 4, since fractional and irrational functions of z cannot be expressed in the integral form a plus bz plus cz squared plus dz cubed plus etc., such that the number of terms is finite. As will be seen in that chapter, in chapter 4, fractional and irrational functions can be expressed as infinite series. Therefore, if the general expression for an integral function given in section 9 included expressions with an infinite number of terms, then there would be no separate categorization of integral functions on the one hand and fractional and irrational on the other. Moreover, Euler later also expresses certain transcendental functions in the form a plus bz plus cz squared plus dz cubed, etc., with an infinite number of terms. In sections 10 to 14, Euler then defines single and multi-valued functions, including infinite-valued functions. Euler gives an example of an infinite-valued function, the arcsine function, and note that Euler considers the whole of the arcsine function, and not just a restricted part of it, as is more usual in modern mathematics. These sections seem to further show that Euler's conception of function was very different to what modern mathematics considers to be a function. As an example, we see, in section 11, a two-valued function of z is a function of the kind which gives two values for any determinate value of z. In modern mathematics, this wouldn't normally be called a function, but rather a relation, since a function in modern mathematics is a particular kind of relation which only yields a single value for each determinate value substituted into the function. Functions of this kind exhibit square roots, such as the square root of 2z plus zz. Whichever value is substituted for z in the expression square root of 2z plus zz, two values result, one positive and one negative. There are a couple of ambiguities here in my opinion that don't really affect things too much, but it may be worth pointing out. Firstly, and maybe a bit pedantically, if 0 is substituted for z, then the two values obtained are 0 and 0, which we may consider on the one hand as the same, but on the other we may consider them as plus 0 and minus 0. We also have the case where imaginary numbers are obtained. We may be able to loosely refer to, say, the square root of minus 1 without a minus sign as a positive imaginary number, and minus the square root of minus 1 as a negative imaginary number, simply due to the absence or presence of a negative symbol. Similarly, for more general complex numbers, we may refer to, say, 2 plus the square root of minus 1 as a positive number, and 2 minus the square root of minus 1 as a negative number, where, again, we're simply making a reference to the fact that the written form of one number contains a positive symbol and the other a negative symbol. And it seems to me that this is probably what Euler intends. It appears that Euler's conception of imaginary numbers includes all of what modern mathematics would call complex numbers, that is, numbers of the form a plus ib. Note also that the square root symbol can evidently mean positive and or negative square roots. What exactly is meant, whether one or the other or both, will depend primarily on the context. Section 12. A three-valued function of z is one which gives, for whichever value of z, three determinate values. Section 14. A multi-valued function z of z is one which gives, for whichever value of z, as many values as the number n contains units. Section 16. If y be a function of z, then conversely z is a function of y. Since y is a function of z, whether single-valued or multi-valued, this gives an equation in which y is defined by z and various constants. From this equation, conversely, z can be defined by y and various constants, and thus because y is a variable quantity, z will be equal to an expression formed of y and various constants, and indeed will be a function of y. Section 17. If y and x are functions of z, then also y is a function of x, and conversely x is a function of y. For the rest of this section, Euler defines odd and even functions and demonstrates some of their properties. I'll quote some of the points, but I won't go into much detail with these sections. Section 18. An even function of z is one which gives the same value whether the determinate value plus k or minus k is substituted for z. Section 19. An even multi-valued function of z is one which gives several determinate values for whichever value of z, yet gives the exact same values whether we put z equals plus k or z equals minus k. Section 21. An odd function of z is a function of the kind which, if in place of z we put minus z, its value also becomes the negative. Section 22. If an even function of z is multiplied by z, or by some odd function of z, the product will be an odd function of z. Section 23. If an odd function is multiplied or divided by another odd function, then the result will be an even function. And finally, at least as far as this video is concerned, section 24. If y be an odd function of z, then conversely, z will be an odd function of y. So now let's move on to chapter 2. Chapter 2, on the transformation of functions. In this chapter, Euler introduces two different types of transformation in section 27. This chapter deals with one type of transformation, and the next chapter deals with the other. The transformations that Euler is most interested in this chapter are factorizations of integral functions and partial fractional expansions of fractional functions. I'll be spending some time going through some of the parts of this chapter in detail, and most of the rest of this video will be concerned with the contents of this chapter. So let's have a look. Section 27. Functions are transformed into other forms either by introduction of another variable quantity or by retaining the same variable quantity. If the same variable quantity is kept, the function cannot strictly speaking be transformed, but every transformation consists of expressing the same function in a different way, and as is clear from algebra, the same quantity can be expressed in many different forms. This chapter deals with the type of transformation which retains the original variable quantity. The next chapter deals with the other case where a new variable is introduced. Section 28. It's often convenient to resolve an integral function into its factors and thus transformed into a product. When an integral function is resolved into its factors, its nature can be more easily determined, since the cases in which the function has a value equal to 0 can be immediately noted. Factors in which no power of z occurs are called linear factors, to distinguish them from composite factors, in which there is a quadratic, cubic, or other higher power of z. Section 29. The linear factors of an arbitrary integral function z of z can be found if the function z is set equal to 0, and from this equation all roots are determined. The individual roots will give the same number of linear factors of the function z. This is of course what's often referred to as the factor theorem. Continuing, if therefore from the equation z equals 0, z equals f is some root, then z minus f will be a linear factor, and thus a factor of the function z. Therefore, after having found all roots of the equation z equals 0, which are z equals f, z equals g, z equals h, etc., the function z resolves into linear factors and is transformed into the product z equals z minus f times z minus g times z minus h, etc. Section 30. The linear factors are, therefore, either real or imaginary, and if the function z has imaginary factors, the number of imaginary factors will always be even. In section 30, evidently, a real factor is a factor which corresponds to a real root, and of course an imaginary factor is one which corresponds to an imaginary root. This section also states that linear factors cannot be of any type other than real or imaginary. I suppose this is effectively expressing the fact that the complex numbers are algebraically closed. The concept of algebraic closure didn't explicitly exist in Euler's time, though the idea was evidently there. We also seem to be dealing with functions with real coefficients, although this is not explicitly stated anywhere from what I can see. Section 31. If Q is the product of four imaginary linear factors, then the product Q can be resolved into two real quadratic factors. For section 31, the idea is that Q has four linear factors, which must be of particular forms, namely 1, 2, 3 and 4 as shown in this section. However, these factors can be paired off in more than one way, and the products may give real or imaginary quadratic factors of Q, depending on which pairing off is chosen. Thus we see that the products of 1 and 2 and 3 and 4 respectively give imaginary quadratic factors, but the products of the pairs 1 and 3 and 2 and 4 give real factors. Therefore, Euler assumes that Q can be factorised into two imaginary quadratic factors and determines from these four linear factors, and shows that these four linear factors can just be paired off in a different way to give two real quadratic factors. All of the expressions in this section can be easily, albeit tediously, verified algebraically. In section 31, Euler claims that the imaginary factors of Q must be of the given forms and that factors of other forms are not possible. This claim can easily be justified by using a bit of simple algebra. Assume that Q has imaginary factors as shown, then the product of these two factors is also as shown on the screen. From the z cubed term we get minus alpha plus beta times the square root of minus 1 minus a plus b times the square root of minus 1 equals a, where a is real, and therefore we obtain the equation minus beta minus b equals 0. And similarly from the z squared, z and constant terms respectively, we get three more equations as shown. So I want to find expressions for alpha, beta, gamma and delta in terms of a, b, c and d. So equation 1 immediately gives that beta is equal to minus b. And now forming the equation 2 times d plus 3 times b, and substituting beta equals minus b, we have as shown. And from equation 4 we have gamma is equal to minus c delta over d. So now substitute this and multiply through by d, giving delta equals minus d. Therefore, since from equation 4 again we have gamma equals minus c delta over d, then gamma is equal to c, and use equation 2 and the values found for beta, gamma and delta, and solve to give alpha is equal to a. So the factors of Q are as shown. And now finally making the replacements, a with 2p, b with 2q, c with r and d with s, then Euler's factors are obtained. And note that the multiplier of 2 for p and q is really to produce simpler expressions for the resulting linear factors 1, 2, 3 and 4. These multipliers of 2 do not significantly alter the form of the factors though. So now let's have a look at the derivation of the expressions for the real quadratic factors which result from the multiplication of factors 1 and 3 and 2 and 4 respectively. I'll do the calculation for the product of 1 and 3, and then the other products can be done entirely analogously. Substituting t and u into 1 and 3 where applicable, we see that 1 and 3 become as shown. And find the product of these two linear factors. And now the transformations shown on the screen can be made. And therefore the product of the two factors 1 and 3 is as shown on the screen now. Which is as required, and similarly for the product of 2 and 4. Now, Euler claims that these factors are real factors. There are two cases to consider. The first is if t is positive or equal to 0, and the second is if t is negative. In the first case, the square root of tt plus uu is always greater than or equal to t, and therefore minus 2t plus 2 times the square root of t times t plus u times u is always greater than or equal to 0. And also 2t plus 2 times the square root of tt plus uu will obviously be greater than or equal to 0. And in the second case, the square root of tt plus uu is always greater than or equal to minus t, where of course minus t represents a positive number, and so 2t plus 2 times the square root of tt plus uu will necessarily be greater than or equal to 0. And also minus 2t plus 2 times the square root of tt plus uu will obviously always be greater than or equal to 0. Thus, whatever the value of t and u, the numbers underneath the square root symbols will be greater than or equal to 0, and so the square roots will be real. Hence, the factors are real quadratic factors, as Euler correctly claims. Note that the square root symbols here appear to be referring to the positive square root. Section 32. If the function z of z has linear imaginary factors, however many, then these can always be paired off so that the product of each pair is real. Section 33. If the integral function z, putting z equals a, gives the value a, and putting z equals b gives the value b, then putting in place of z values between a and b, the function z will attain any intermediate value between a and b. This is of course the intermediate value theorem for integral functions. And I suspect that Euler's proof of the statements of section 33 would probably not be completely acceptable as a rigorous proof in modern mathematics, but would certainly suffice as a kind of justification. Many of the techniques that Euler uses would not be sufficiently rigorous for modern mathematics, but that doesn't mean that the conclusions that Euler arrives at are wrong. Simply the results that he obtains are not as generally valid as we might initially hope. Euler's proofs, though flawed by modern standards, almost certainly in many cases pointed the way towards more rigorous proofs further down the line, by giving a good indication of the general ideas behind the proofs of the results. Section 34. If in the integral function z the greatest power of z is an odd number, 2n plus 1, then the function z will have at least one linear real factor. In the proof of the statements in section 34, Euler, again, uses methods and techniques that would not be considered properly acceptable in modern mathematics. In this proof and several times throughout the book, Euler treats the symbols for positive infinity and negative infinity, whatever is meant by these terms, in the same way that he treats symbols representing integers or real numbers. In this proof, for example, Euler directly substitutes the symbol for infinity into expressions, and this would clearly be unacceptable in modern mathematics without due consideration. Nevertheless, it doesn't make Euler's results and deductions wrong, it just means that the reasoning used is, at least from a modern perspective, flawed, and that this technique of direct substitution of infinity into expressions shouldn't be done without sufficient care. Euler does take into consideration the fact that these numbers have some peculiar properties, namely that the greatest power of infinity utterly overwhelms any lower powers, reducing these lower powers to insignificance. I think that when Euler makes these substitutions, he is possibly getting at the modern notion of limit, but unfortunately didn't have the notation to properly articulate the idea at the time. Of course, there was no well-developed theory of the infinite in Euler's time. Section 35. Therefore, the integral function z, in which the greatest power of z is an odd number, will have one real linear factor, or 3, or 5, or 7, etc. Sections 36 to 37 give some more properties of integral functions where the greatest power of z is an even number. Section 36. The integral function z, in which the exponent of the greatest power of z is an even number, 2n, has either two real linear factors, or 4, or 6, or etc. The statement of this section seems to be assuming that if such an integral function has any real linear factors at all, then there must be an even number of them, because of course it may be that an integral function, as described, may have no real linear factors. Section 37. If in the integral function z the exponent of the greatest power of z be an even number, and the final term, or constant term, has a negative sign, then the function z has at least two real linear factors. Section 38. If in a fractional function the variable quantity z has a dimension equal to or greater in the numerator than in the denominator, then this function can be resolved into two parts, one of which is an integral function, and the other fractional in the numerator of which the variable quantity z has dimensions smaller than in the denominator. Section 39. If the denominator of a fractional function has two distinct factors, then this fractional function resolves into two fractions, of which the denominators will be respectively equal to the two factors of the original fractional function. The factors here are not required to be linear, merely distinct. The example that Euler provides shows that he does not assume the factors in the denominator of the original fractional function to be linear. However, we have the statements of the next section. Section 40. The fractional function m over n can be resolved into as many linear fractions of the form a over p minus qz as there are distinct linear factors in the denominator of n. Of course, here we're going in the direction of partial fractional expansions, and the remainder of this chapter deals with partial fractional expansions of different forms, along with several examples to illustrate how the expansions may be practically obtained. For example, section 42, a fractional function of the form p over p minus qz to the power of n, where in the numerator p the greatest power of z is not as great as that in the denominator p minus qz to the power of n, can be transformed into partial fractions of the form as shown, in which all numerators are constant quantities. This deals with the case where we start with a fractional function which has a denominator of the form p minus qz to the power of n. Section 42 merely states what is the case, but it doesn't explain how the partial fractional expansion can be practically found. However, section 45 gives a practical method for finding the values of the constants a, b, c, and so on. Section 45. If the denominator n of the fractional function m over n has a factor p minus qz to the power of n, the partial fractions which thus arise as shown can be found in the following way. And the examples in this chapter, of which there are quite a few, illustrate how the partial fractional expansions can be practically obtained. And this seems like a reasonable place to end this video. If you have any questions about anything in this video, or if you have any suggestions for future videos, then please get in touch. Thank you for watching, and don't forget to subscribe and click the like button, and I'll see you in the next video.